Let's work some examples where we use polar coordinates to find the, the double integral of various functions. For our first problem, problem 7, we're trying to find the double integral of x squared y over some region. The region here, this D, is the top half of a disk with center the origin radius 5. And I'm going to go ahead and just draw that. So we're not going over the entire disk, we're only looking at this top one. There's a radius of 5. We want to be able to work with this disk, or this half disk, and find this double integral. Now, what are we going to do here? Well, we're going to remember that what we're really looking at is all the points r theta, where the radius from the point, the distance from the point to the origin is either 0 when it starts at the origin or 5 when it gets to the edge of the disk. So the r is going from 0 to 5. Theta, on the other hand, if we were going around the entire disk, we'd go 0 to 2 pi. Since we're doing only half of it, we're going from 0 to pi. So pi is over here at this side. This is actually a polar rectangle, even though it maybe it looks less like a rectangle than we even think of it. So when we were drawing polar rectangles before, I was generally making them look vaguely rectangular up in one quadrant. But as long as they have this form here, where r is between two values and theta is between two values, then they're still a polar rectangle. So we can use the formula for a polar rectangle. So the double integral over d of this function. So we put the theta values first. We're going from 0 to pi. Then we put the r values from 0 to 5. Now we do have to go ahead and replace x and y with our formulas. So remember our formulas here are x equals r cosine theta and y equals r sine theta. We're going to have to replace x and y by those expressions. So x squared is r cosine theta squared. Y is r sine theta. Now remember, we do need this extra r. Then we do dr and d theta. We'll go ahead and rearrange some stuff here. So here we have, well, actually 4 copies of r. We have 2 copies of cosine, and we have 1 copy of sine. When we integrate with respect to r, the cosines and the sine are just constants, so we don't have to do anything with those. So we have the integral of r to the 4th is 1/5 r to the 5th. That's going to go from 0 to 5. We could put the cosine squared and the sine inside there, but I'm just going to pull them out. This thing here, so when we plug in 5 to the 5th divided by 5, that's actually the same thing as 5 to the 4th, which is 625. When we plug in 0, obviously it's 0, so I'm going to pull out that 625. And now let's focus on integrating the cosine squared sine with respect to theta. That one, you might have to think about how to do that. But what we're really going to do here is make a substitution. We're going to set u equal to cosine. That means that du is negative sine d theta. That sine there is going to help us. In general, that we might not have something like that. We might have to fall back on some other formulas from back in Calc 2. So remembering all the ways we dealt with, say, products of trigonometric functions. But we're really here going to be integrating, well, we're going to have a negative for 1, but then we're integrating u squared. What is the integral of u squared? Well, that's actually just 1/3 u cubed. And I'm kind of shortening this because I ran out of space, but hopefully you can kind of tell what we're doing here. The limits, the new limits, when we plug in 0 in for into the cosine, we get a 1. When we plug pi into cosine, we get a -1. We go ahead and just work this all out. So 1/3 times -1, -1 cubed is a -1/3, minus 1/3 times 1 cubed is another -1/3. So we end up with a -1/3 minus 1/3. Obviously, the negatives didn't really matter. We expected to get a positive thing. But we end up getting basically 2/3 times 625, which comes down to a very big fun number of 1,250 over 3. And you could write that however you want to. But the point is that we are able to compute that particular value. Moving on to problem 9, we have a very similar kind of problem. We have a double integral of some function, sine of x squared plus y squared, where R is the region in the first quadrant between the circles with center of the origin and radii 1 and 3. So again, if we draw this out, and I'm going to try to take up less room with the drawing this time, but still have enough to really see what's going on. So we have a radius of 1 and a radius of 3. And it's the region between those two circles. But we're only looking at the stuff in the first quadrant. So only this portion of it. Really, it'd be an annulus if we were to go the whole way around. Of course, that region R is the set of all points r theta, where r it goes between 1 and 3. Theta is going between 0, and because we're stopping at the first quadrant, we go up to pi over 2. This, again, is a polar rectangle. That's going to make the whole thing not too bad to do. Not that it gets super complicated to do other ones. But remember how we set this up. So we start off, we look at our theta values. So theta is going from 0 to pi over 2. So 0 to pi over 2 is our first integral. Our second one, r, is going from 1 to 3. Now we need to plug in our values for x and y. So remember, x equals r cosine theta, y equals r sine theta. But there's a reason why I actually reminded us of other formulas. Remember, we also have the formula x squared plus y squared equals r squared. If we can make use of this formula, if we see an x squared plus y squared, we should immediately think of r squared rather than trying to plug them in. If you plugged in r cosine theta and r sine theta, you just use the fact that sine squared plus cosine squared equals 1 and simplify it. But there's no reason not to do it the easy way. So when I look at this, I think of actually it's a really good rule of thumb that when you see an x squared plus y squared, polar coordinates is actually frequently an easy way of handling those kind of functions. But the point here is I have sine of r squared when everything is said and done. Now, of course, we do have the r, the dr, and the d theta. Don't forget that r. In fact, this would be a very nasty problem to do if we didn't have that r. Because what we can kind of already see here is that because we have the r squared inside of the sine, we would like to do a substitution. I'm going to substitute u equals r squared, which means that du is 2r dr. Of course, the 2 here, we had to turn into a 1/2. but we'll have a 1/2 sine of u du d theta. This integral here, well, we have to plug in 1 and 3 into r squared, so we get 1 and 9. I guess one thing I didn't mention before, and probably should have done that right away, since there's no thetas in our integrand, the d theta here, we could actually kind of split this up. We could split this up as the integral from 0 to pi over 2 d theta times the integral from 1 to 9 of 1/2 sine u du. And in fact, this just turns into pi over 2. This part over here, actually I'll pull out the 1/2, but the integral of sine is negative cosine. We're taking that from 1 to 9. If we combine those, we get a pi over 4. And then here we have, well, we'll have cosine of 9, but with a negative, minus the cosine of 1 with a negative. We'll just swap the orders of that. We'll have cosine of 1 minus cosine of 9. So there's not really any more simplification we can do here without just plugging into a calculator. 1 and 9 are not nice numbers for when it comes to radians for cosine. So we'll just kind of leave it like it is. But the point here is being able to actually just do the integration. The process is the important part. In problem 15, we're going to return to that rose curve that we looked at before, though this will actually be a slightly different rose curve. There we looked at cosine of 2 theta. Here we're going to look at cosine of 3 theta. And rather than me drawing this out, let's go ahead and graph it in GeoGebra. So again, GeoGebra doesn't really just allow me to plug in a polar curve just directly. I need to turn this into a parameterized curve. So basically, I'm using the formula x is r cosine of theta, y is r sine of theta, where my theta value is going to go from, well, normally we'd go 0 to 2 pi if we don't see any other. If we don't see a reason not to, I'm going to go ahead and do 0 to pi this time because it will actually give me the entire curve. The r I'm going to replace with my formula. So this was r of 3 theta. R is cosine of 3 theta, sorry. And then here, same, r is cosine of 3 theta. If I graph that, it gives me this curve here. Now, if I were to go from 0 to 2 pi, it actually would trace out this curve exactly the way it is again. So actually, I don't get anything new from that. And then what are we actually trying to do in this problem? We're trying to use a double integral to find the area of one loop. So say we just want to find the area that's contained in this loop here. Now, we do need to figure out how to actually just capture a single loop of this, which actually will turn out to be, we want to find out when does this curve hit the origin. Essentially, we want to find out where do we start here and end here, and what angles are being contained in that. Well, it turns out that if we take our curve and we plug in pi over 6, we end up right at that point. And the reason being is that if I plug in pi over 6 into cosine of 3 theta, I'm actually getting cosine of pi over 2. And so I'm really just looking at, well, cosine of pi over 2 is 0. Similarly, if I plug in, say, a of minus pi over 6, I also get 0. And as I put in values between negative pi over 6 and pi over 6, I trace out this curve. And so those are the limits that we're going to use. We're going to say theta is between negative pi over 6 and pi over 6. What can we say about the r values? Well, we're just going from our origin out to the curve. We're looking at various radii starting from our origin out to the curve. So we're going to say the r values are going to go from 0 to cosine of 3 theta. And in fact, that's what we're saying. Our loop, which we'll call D is our loop, is just the region. It's the collection of all points r theta, where theta is between negative pi over 6 and pi over 6, and r is between 0 and cosine of 3 theta. We're looking for the area of that region. Now, why are we talking about areas, though? Aren't we really talking about volumes when we're doing double integrals? Well, one trick is to use a double integral by looking at the double integral over our domain of the number 1. Because what this really does is it takes the function f of x y equals 1 and finds the volume underneath that is contained in that region. You can kind of think of it as a cylinder with height 1 and the base being d. And the volume of such a thing should just be this 1 times the area of that base. So the area of the base is just that double integral. And that allows us to use the information that we've just been talking about in this section to find the area of that base. So once again, here we have limits on our theta and r. We'll go ahead and put the limits of theta over here, and then we'll put the limits on r. This is our first one where we actually do have not both numbers for r, but that's okay. One advantage of doing this, we do just get to put in 1. We don't have to replace x or y because we're just getting a 1 in here. But we do have to remember that extra r. That extra r still needs to be in there. So we're really going to be integrating r with these conditions. Now, we don't have any thetas in the integrand, but because we do have thetas in our limits, we can't split this up. But we're just going to go ahead and integrate r. Obviously, the integral of r is 1/2 r squared, going from 0 to cosine of 3 theta. That means, well, when we plug in 0, we don't get anything. When we plug in the cosine, we do end up having to integrate, well, let's move the 1/2 out here too. We have to integrate cosine squared of 3 theta. Now, we do have to remember how to integrate something like that. When we have cosine squared, how do we integrate that? If you don't remember, I suggest you go back and review some of this stuff. I think this is in sections, in chapter 7. Yeah, it should be section 7.2. Various ways of integrating powers of sines and cosines multiplied together. So this would be an example where we don't have any sines, but we do have an even number of cosines, and we have to remember that in such a situation, we want to use a formula, one of our double angle formulas, or well, I guess power reduction formulas was what we're calling it. So here, if we have cosine squared of some angle, I don't want to use theta just because I want to keep it distinct from that, but let's just say t. Cosine squared of t is equal to 1/2 of cosine of 2t plus 1, if you recall that formula. Actually, I'm going to go ahead and replace cosine squared of 3 theta. I'm going to use the 3 theta in here for t, but I'll go ahead and pull out that 1/2. So we'll have a 1/4 integral from negative pi over 6 to pi over 6 of cosine of 6 theta plus 1. Well, the integral of cosine of 6 theta is 1/6 of sine of 6 theta. Integral of 1 is theta. I'm going to take that from pi over 6 to pi over, negative pi over 6 to pi over 6. Now, one nice thing here, and if you ever do another one of these where you're using a different number here, this will always pretty much be the same when we find the area of one loop of one of these Rose curves. When we plug these limits into the sine, we're going to have sine of negative pi and sine of pi. Both of those are equal to 0. So actually, we don't even get anything from the sine portion in our formula. But we do actually get something from the theta portion. This plus 1 actually turns out to be the most significant part of the process. We actually end up getting a pi over 6 minus a negative pi over 6. So we end up getting that. A 1/4 times pi over 3 is a pi over 12. That is the area inside this loop. One last example in this video, we're going to find a volume using polar coordinates. So here we're going to be dealing with the paraboloid z equals x squared plus y squared, but we're going to use a domain of the disk x squared plus y squared is less than or equal to 25. Basically the disk of radius 5. We want to find the volume that's underneath that paraboloid. Of course, we can go ahead and graph that paraboloid if we want to take a look at it. So we have this thing here. If we want to, we could also graph the disk. I'm just going to graph the circle that's going to be our... Okay, graphed as a cylinder. I guess we kind of thinking about what is the volume underneath this paraboloid that is contained in this cylinder. Of course, that's really hard to see because we end up with having a very... It to go up very high before it even exits that cylinder. But we've got this region that's underneath that paraboloid, inside that. It's going to be it's actually going to be a pretty big number just because we have to zoom out so far. But at least we've got an idea of what we're actually looking at. Now, when we actually want to do this using polar coordinates, we want to think about what is our region that we're working with basically as a polar rectangle. In this case, it actually is a polar rectangle. So I can even just put as r. The r here is all r and theta, where r starts at 0 but goes out to 5, because that's our biggest radius here is 5. Of course, because we're going around the entire disk, our theta will just take from 0 to 2 pi. A very simple polar rectangle, which is the whole point. This disk would actually be kind of annoying to work with if we were not dealing with polar coordinates. But in polar coordinates, it's very simple. So our volume, which of course is the double integral over this thing of our our function here is just x squared plus y squared. In polar coordinates, we have 0 to 2 pi for our theta. We have 0 to 5 for r. Our function here, remember, x squared plus y squared is equal to r squared. So we have r squared for that part. We have an extra r from our formula for polar coordinates. Then dr d theta. So actually this turns out to be a really simple problem because now we're just integrating r cubed. In fact, there's no thetas in here and there's no thetas in our limits. So we can actually kind of take out the integral from 0 to pi, or sorry, 0 to 2 pi d theta, and that just becomes a 2 pi on the outside. What is the integral of r cubed? Is this going to be a 1/4 r to the 4th? We get to take 5 to the 4th power again, unfortunately, but we have a 2 pi times 1/4 times 625, then minus 0. Or in other words, we can cancel out a 2 from top and bottom. We get 625 pi divided by 2 as our answer. That is the volume underneath this paraboloid, inside of that circle. So I'm going to go through a few more problems in the next video. Just kind of don't want these videos to go on too long, and we're kind of pushing it already, getting close to half an hour. So I'm going to leave this video here, and I'll see you in the next one.